We previously discussed the concept of conservation of momentum. We will soon see that there is another very powerful conservation principle in physics called the conservation of energy. It states that there is a certain quantity called energy that remains unchanged in a system, except for any that flows in or out of the system. It's hard to say exactly what energy is. It's an abstract quantity that we count up in a certain way. When calculating the energy of a system, we must keep careful track of any energy that enters or leaves the system. There are also a number of different forms of energy: kinetic energy, gravitational energy, elastic energy, electrical energy, heat energy, and others. Each of these has its own formula for calculation. If you sum all these energies up for a system, the total will remain unchanged except for what goes in and comes out. It turns out that using energy rather than force, one can construct a complete system of mechanics that is fully equivalent to the Newtonian system. This was done by Lagrange and Hamilton, and you may encounter their system in the future if you take more advanced courses in physics. However, even in the Newtonian system, energy remains a useful concept. This week, we will discuss kinetic energy, the energy associated with the motion of a mass, and also the concept of work, which allows us to calculate how the action of a force changes the kinetic energy. We will see that the work done by a force is calculated by evaluating an integral that, in general, depends upon the specific trajectory or path taken by the object or system. However, we will also see that there is a special class of forces called conservative forces, for which the work integral is path independent and instead depends only on the starting and ending points. Finally, we will discuss examples of both conservative and non-conservative forces.
Let's talk about kinetic energy. We're calling kinetic energy K, and it's given by 1/2 mv squared. And this is a scalar quantity, so it's going to be either 0 or positive. It's never going to be negative. The SI unit for kinetic energy is joule. So we have 1 joule here for kinetic energy, and the units come from this. So we have kilogram and then meter per second squared. Now let's assume we have an object that is first at rest and then it speeds up with a certain velocity, which means the object is going to experience a change in kinetic energy. And so we'll express this as 1/2 mv final squared minus 1/2 mv initial squared. And if we have a motion, so velocity in let's say a 2D or a 3D space, then we can then we have to consider all these components here, and we can also pull out the 1/2 m, and then we have v x final squared plus v y final squared plus v z final squared, and then minus all the initial values, x initial, y initial, and z initial. Now, when we consider just a point particle, then we can also ask, what is the momentum? How can we pair up momentum and kinetic energy? So I'm writing it again here. K equals 1/2 mv squared. If we multiply this by m upstairs and downstairs, we're going to have m squared over v squared, and that's actually p squared. Remember, p equals mv, and so we're going to get that this actually can be expressed as p squared over 2m. And so that is the kinetic energy expressed in terms of the momentum of a particle.
Suppose we have an object and we're applying a constant force in the horizontal direction. We would now like to introduce the concept of work. Suppose our force starts at a point xi and goes to a position x final, and we'll call this the I hat direction. then our force as a vector will write Fx I hat. And now what we'd like to calculate is the product of force with the displacement of the object. So our displacement vector, delta x, is equal to delta x I hat, where delta x is equal to x final minus x initial. And for our constant force, for the case where Fx is a constant, we would like to define the work done by this force in displacing the object from our initial position, and we'll mark it like that, to the final position here, is given by the product, so we'll call work, is the product of the force, Fx, times the displacement, and so that's equal to Fx times x final minus x initial. And this is our definition for work for the special case where the force is constant. Now, if we look at this, our force may, in our diagram, we drew it in the positive x direction. But if our force, Fx, were less than 0, and our displacement was in the positive direction, positive, then you can see that the work is negative. So if the force is opposing the displacement, and that's what would happen if Fx was pointing in the negative direction, the work would be negative. If Fx is positive and the displacement is positive, then the work is positive. So we see work is a scalar that has a signed quantity, positive or negative. Now, whenever we introduce a new quantity, we always have to be a little bit careful about the units. Since work is the product of force and distance, then our SI units for work are the units of force, which are newtons, times the units of distance, meters, and we call this a joule. So 1 joule is equal to 1 Newton meter. Now, graphically, we can make an interpretation of this. Let's draw a graph of force, the x component of the force, and here, if we had some origin, we'll have x. And our object is starting at xi, and it's going to x final. And throughout this process, we're assuming that the force is constant. So what we see in this diagram here, I'll just shade in this area, that our work, which was the product of force times the displacement, corresponds to the area here. So we have a geometric interpretation of work as the area under the force versus position graph. And this is our example of work for a constant force. We already defined work in one dimension as the product of force times displacement for a constant force, but now let's look at a case where we're applying a force F that is a function of x. So our component, f of x, is a function of x in the I-hat direction. And one of the simplest examples of a force like this is what we call the spring force. Now, when we apply this force to our object, and let's look at an object I-hat direction, we'll have an origin, and this is our plus x coordinate system. Now, when we apply a force, what we want to look at is, because the force is a function of position, then we want to look at the displacement over a small amount. So let's call this the point xj. And out here, let's refer to this as xj plus 1. And what we've done is we're going to ask how much work is done when the force is displaced from here to there. And that's what we'll call delta x. So now our displacement is a small displacement, x of j plus 1 minus x of j. And our work for this small displacement, and that's why we'll indicate it with a delta, is equal to the force, which is a function of x, times this displacement. And so now we get f of x times x of j plus 1 minus x of j. And what we have to indicate here is because the force is varying, we're looking at just this displacement here. Let's refer to this force as in the jth part. Now, the total work is just the sum of all these scalar quantities. Remember, although force is a vector and displacement is a vector, the product of these two quantities is a scalar. And so if we want the total work, we have to sum, from j goes from 1 to n, of this quantity f of j dot, and I'll put a little j there to indicate that, delta xj. Now, what does this sum mean? Well, imagine that we're making a series of displacements all the way out to a final position, x final, and we divided this interval into n pieces. And so this now represents the little bit of work done for all of these displacements. And that is what we define to be the work for a non-constant force. Now, the issue here is about how fine we cut this interval in. We made n individual pieces. But if we want to ask ourselves what is the limit as n goes to infinity, then that's what we now need to consider. So what we're doing is we're making smaller and smaller and smaller little displacements, and we're taking this sum, j goes from 1 to n, of x of xj times delta xj. And this limit of a sum is, by definition, the integral of the force with respect to dx. So what we end up with is our work is the integral of f of x. Now, it's a function, and I'm going to have an integration variable x prime of dx prime, where x prime is going from our initial position to our final position. And this is now our definition of work, which generalizes a constant force to a non-constant force. Now again, let's try to look at some type of geometric interpretation. So if we plotted f of x versus x, and now let's consider a case where we have some arbitrary force. So I'm going to just draw the force as if it were arbitrarily increasing as a function of x. And here's our x initial, and here's our x final. And again, we would like to make a geometric interpretation. Let's consider xj, and I'll make this very big, xj plus 1, for the sake of visualization. And this value here is f of xj. And so what we see now is that little bit of work, like we had for a constant force, can be approximated as the area underneath the curve for just this small interval between xj and xj plus 1. And if we make this sum, what we're doing is we're just taking a series of approximations to the area under these curves. Now you can see graphically that there's very little error when the function was nearly constant. But in this position where the function is growing, this represents our little error. However, in the limit, as n goes to infinity, we can make that error go vanishingly small. So once again, we see as a geometric interpretation that this is the area under the curve of the force versus position between the points, the initial xi and the initial and the final x final, where the particle is being displaced from an initial position to some final position. And here we can call our initial position anywhere we want. If I write that as x initial to the final position. And that's our generalization of the definition of work. I'd like to now show you two mathematical facts about how we integrate quantities of motion. Suppose we have an object, let's call this the I-hat direction, and it's moving, and it has an x component of velocity. And suppose it starts at some initial position and goes at some final position. And in the initial position, it was at time ti. and the final position was at t final. Now, we have two very important integrals that we want to look at, which govern how we describe, how we integrate acceleration with respect to time, and also how we'll integrate acceleration with respect to space. Now, recall that our acceleration, which may be a function of time, is the derivative of the x component of velocity with respect to time. So let's first look at a simple integration of acceleration with respect to time and see what we get. So if we integrate acceleration, now I'm going to introduce an integration variable, dt prime, and our integration variable goes from our initial time to some final time. And if we use our fact that acceleration is the derivative of velocity, then we can write this as dvx dt prime again. After a while, I'll drop the dummy variables and the endpoints of the integral, and this simply becomes the integral from t prime, t initial, t prime equals t final, of dvx prime. Now notice we've done a change of variables in the integration. So instead of now talking about the endpoints of the integral from t prime, t initial to t final, now what we're doing is we've changed our integration variable. And so what we have is we have the velocity integration variable is going from some initial value, and that integration variable is going to some final value. So again, our initial conditions may have some initial velocity and some final velocity. Three different ways of describing the initial and final states. This integral is a very straightforward integral, vx final minus vx initial, which is the change in the x component of the velocity. And that's our classic result that we've done, that the integration of acceleration with respect to time is a change in velocity. Now, let's see what happens as a comparison when we integrate our acceleration, not with respect to time, but suppose that it's a function of space. And so now we're integrating again. We have a dummy variable. We have to be careful because this is the x component of acceleration, but x prime is our integration variable, and that's going from some initial position to some final position. Now, we can write this as, again, make the substitution vx dt dx prime, going from the initial to the final. But now, notice we're going to rewrite this integrand as dvx times dx prime dt. And when we do that, we have this result that dx prime dt prime is precisely what we mean by vx. Now, I'll introduce some dummy variables there as well. So what our integrand becomes is dvx prime vx prime. That's not a function. It's a product of an integrand, of a differential times vx prime. And now our new integration variable is going from some initial value to some final value. Once again, this is a straightforward integral. For those who haven't seen integrals like this, it's just something like x dx is x squared over 2, but our integration variable is vx prime. So what we get is 1/2 vx final squared minus vx initial squared. And so what we see here is two fundamentally different facts, that if you integrate acceleration with respect to time, you get the change in velocity. But if you integrate acceleration with respect to space, you get 1/2 times the change, not of velocity, but of the x component of the velocity squared. And both of these facts are central to how we'll analyze the concept of work and how we applied Newton's second law.
We're now going to derive the work-energy principle. We're going to do so by using Newton's second law, but we're not going to consider it with respect to time as what we've previously done, but we're now going to consider it with respect to space. So F equals ma, and we're going to take the x component of that, and now we're going to integrate this. So f x dx prime, and it runs from x prime equals x initial to some final value. And then over here we have we're going to pull the m out, m integral, and it also goes from some initial to some final value. And we're going to have ax dx. We have previously shown that this integral here is 1/2 v final squared minus v initial squared. And if we're going to plug this in here, we're going to get that this expression is 1/2 m v final squared minus v initial squared. And you should recognize this term. This is the change in kinetic energy. And what we have here on the other side, this integral fx dx is defined to be the work. Work done on the system, which we're going to call W. And that work done on the system is its change in kinetic energy. So this is the work energy principle.
Let's consider the motion of an object that is under the action of a force. So we have some force that's acting on this object, and we have a little displacement ds. So this is a small displacement of the object. Then we know that the small amount of work done by the action of this force is f dot ds. And the rate of doing work, so let's now introduce the concept of power, which is the rate of doing work. That is f dot ds over dt. And ds dt is just the velocity of the object. So we see very simply that when we talk about power, and sometimes people use the symbol p, although we can also talk about pressure and momentum, so it's a little bit tricky. But here, the power is f dot v. And power is a concept that will appear in many different settings.